Hello, is my screen visible? Hello, am I audible? Start. Hello, good afternoon to all. Welcome to the second week tutorial session of NPTEL course, Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I do this problem solving session as part of my PMRF TA duty. In the previous week, we had seen a few questions regarding the recap of basic thermodynamics. In this week's session, we will actually try to extend the analysis. We'll look into the vapor power cycle and a steam power plant. Basically, steam power plant, Rankine cycle kind of things. We'll see a few problems, numerical type as well as multiple choice questions in this week. So we can actually move into the questions right away. So first is a multiple choice type question. I'll look into it and try to solve. I'll also try to solve within a minute. That's a question. What is the overall change in the internal energy of a steam power plant? Is it negative, positive, zero, or more information required? So it's a straightforward question. The answer is zero. The answer is zero. So the question is regarding internal energy and it's a property. So we know that steam power plant operates in a cycle. So anything that operates in a cycle, when a property undergoes a cycle, its total change will be equal to zero. So for the cycle, we could say that delta Q is equal to delta W for the cycle. So since internal energy delta U is a property, U is a property, so delta U value will be equal to zero. So you could see what you could say is that delta Q is equal to delta will be equal to zero. So zero is the answer. That was a simple question. So we'll move to the next question. It's a small numerical. A small insulated nozzle causes a drop of 0.7 kilojoule per kilogram in the enthalpy from the inlet to the exit. If the kinetic energy of the inlet is negligible, what will be the stream velocity of the exit? Four options are given, so we need to calculate the velocity at the exit of the nozzle. Look at it. I'll also try to solve it in a minute. So have you tried to solve the problem? Am I audible? Okay, the question is regarding a nozzle with an enthalpy drop of zero point 0.7 between the inlet and exit. If the kinetic energy of the inlet is negligible, we need to find the velocity at the exit. So basically, we have to take into consideration, since it's an open flow device, we have to take into consideration a steady flow energy equation. So if you write the steady flow energy equation, we can denote in terms of the enthalpy, the velocity, kinetic energy based, and then the potential energy. Uh, is equal to enthalpy. This is basically U plus PV term, or the energy plus the flow work term. That will give you the enthalpy, V2 square divided by 2000 plus GZ2. So we can neglect kinetic and neglect potential energy in this problem because nothing is given. So we can assume both of them are the same altitude or elevation. And then the difference in the enthalpies are given H2 minus H1 or H1 minus H2. This is a pressure drop. There's an enthalpy drop. So H1 minus H2 is 0.7 kilojoule per kilogram. And that will be equal to V2 squared divided by 2000, because in the problem it's given that at the beginning the kinetic energy of inlet is negligible. So from this we can get the value of the velocity at exit. So V2 will be equal to uh, root of 2000 of delta H, that is 0.7. That will be equal to 37.4 meter per second. So if you note one thing, we have written this steady flow energy equation in terms of kilojoule per kilogram. So this H will be usually in terms of kilojoule per kilogram. In problem, it will be given as kilojoule per kilogram. So correspondingly, we have to change the other two parameters accordingly. So the mv squared by 2 will be the kinetic energy, but to get in terms of kilojoule, we have to divide it by 1000. So that's why the bottom 2000 term, 2 into 1000 basically, and then be divided by mass to get in terms of kilojoule per kilogram. And similarly, you have to divide this GZ1 divided by 1000 as well. So since we have ignored it, I haven't mentioned that in this particular problem. So that will give the enthalpy change in terms of the velocity squared divided by 2000 will be in terms of the same unit as that of kilojoule per kilogram, and from there we can straight away calculate. So the answer is option B. Yeah. Do you have any questions? You can write it in the chat box if you can, or if you want. If you do not have an audio jack connected to your device, or mic in. So I meant to say mic. If you don't have a mic connected to your device, you can actually write it in the chat box. So any clarifications required? Look into the third problem. This is regarding a steam power plant. I'll read through it. A steam power plant operates on the power plant cycle. If the isentropic efficiency of the turbine is 87% and isentropic efficiency of the pump is 85%, determine thermal efficiency of the cycle, the net power output of the plant for a mass flow rate of 15 kilogram per second. It's a straightforward problem. Try to approach it. Meanwhile, I'll also solve within another couple of minutes. So I'll try to solve it. It's a case of a steam power plant. So before approaching the problem, I'll try to draw the schematic of how the total cycle happens. So first of all, if you consider point 1 to be the place where we pressurize the fluid or we create sufficient pressure difference that is this pump. It starts 0.1, 10 kilopascal and 38%, 38 degrees Celsius. So the reason why I asked you to do is this, because the problem requires the state points. So without that, we can't try to solve it. So this schematic will make it that clear for you. So before the starting of pump, it will be 10 kilopascal, 38 degrees Celsius. And then after compression, it will become 1 megapascal. And then it goes and it's get heated up, goes into a boiler. Uh, and this is pump, and the isentropic efficiency is given as 0.85. So I beg your pardon, this is not for 1 MPa. This is not required. This is not required. Okay, and this is 15 MPa, 15 megapascal, and the temperature of the inlet is 35 degrees Celsius. For the time being, assume it to be the case. Then it gets heated up, becomes superheated, and the pressure remains the same, constant pressure process, 15 MPa and 625 degrees Celsius. And this is state point 2, and this is state point 3. (15 megapascal), then turbines, where the high pressure steam will be expanding to produce work. Then efficiency of the turbine is 0.87, and then 0.4 will be at the exit, and it will be at 10 kilopascal. And then there will be the condenser, where the steam, the vapor will be converting into the liquid form at constant pressure at 10 kilopascal. And it comes back to the point what, that is the point before the pump, before it pressurizes, before it pumps the fluid into a higher pressure. So basically, what's the difference between a compressor and pump? A compressor actually is used for airflow, where it actually compresses the fluid. So basically, compression process means reduction of the volume and increasing the pressure. So there will be a change in enthalpy in the process when it moves from a lower pressure to a higher pressure. It compresses, basically volume changes, and there will be a change in enthalpy. So work input required in the case of a compressor could be written in terms of the change in enthalpy. But in the case of pump, you do not actually compress the fluid. It's basically so incompressible liquids and other fluids. And in this case, the input work that is required for a pump can be written in terms of the specific volume at which it happens multiplied by the delta P. So there will not be a change in volume as such in this case. So we can't apply the same for a compressor because there will be a change in volume. There will be a change in volume as well as there will be a change in pressure. So you have to account the change in work in terms of the input work in terms of change in enthalpy for a compressor. But for a pump, you can straight away assume since the change in the specific volume is very minimal, you can assume that the specific volume multiplied by the delta pressure between the lower point and the upper point will be giving you the input work. Similarly, in the case of turbine, uh, it's a high pressure steam. So you can't apply any of these to get the work output. So you have to account that in terms of the enthalpy, change in enthalpy of a using the steady flow energy equation. If you try to represent this in terms of a TS diagram, an ideal cycle. So there will be a constant, there will be an isentropic pumping process 1 to 2, and then there will be heat addition in the boiler, constant pressure process, heat input, which is a point 3. Then there will be this isentropic process where it expands in the turbine and then the condenser, heat rejection. So turn in the pump and the work given out of turbine. This is the ideal case, but in our case, an efficiency is given, isentropic efficiency is given for both the terms, for both pump as well as for both the pump as well as turbine. So this will be the new state point 2 dash to take into consideration the irreversibilities that occurs. And then this is the, in fact, I should have drawn it in the other way, where the dotted line should represent the isentropic process and actual line should be represented by a solid line. So this can be point 2 dash, and this will be 3 and 3 dash point. So the real point might be this is 4 and 4 dash. The real point at the exit of the turbine expansion will be slightly towards the right compared to the isentropic case. So you have to actually determine that using isentropic efficiency that is given in the problem. So we can try to solve it straight away. You have to determine the thermal efficiency of the cycle first, and then the net power output of the plant for the mass flow rate of 15 kg per second. So it's a straightforward problem. First, we have to calculate the thermal efficiency of the cycle. The thermal efficiency is given as the work net, the net work output from the cycle divided by the heat input Q in. This is in the boiler. So work net, rather than finding the work net as such, we can uh, rather than finding this using the analogy where the net heat input will be equal to the net work that will be done for a cycle, we can actually try to get it from the turbine work and the compressor work, assuming that there is no work happens, there's no work output in the boiler as well as or work exchange between the boiler and the condenser. So we assume it to be a pure enthalpy change process that will be accounted in the heat transfer in the boiler as well as in the condenser. So there is no work associated with these two terms. So the network will be associated with the only two components, that is a turbine as well as a pump in this case. So you can write it as work of the turbine, that is a positive work, and then the work of the pump, that is a negative work, that is heat given into the work given, the work input to the system. So doing. So it's kilojoule per kilogram. So there should not be dot. Dot corresponds to the rate when you multiply it with the mass flow rate of the steam within the cycle. So first of all, we have to calculate the turbine work. So the turbine work will be equal to WT. That will be equal to the change in enthalpy between the process 3, 4 work turbine, that is a work turbine isentropic multiplied by the isentropic efficiency. So the actual work will be less than that of the ideal work. So this is the ideal work if it was an isentropic one. So basically that means I can represent it in terms of efficiency, isentropic efficiency, and as well as the enthalpy change. So this could be written as H3 minus H4. So H4 is the isentropic enthalpy at the state point 4. So isentropic exit of the turbine, you'll get the enthalpy that will be H4. So H3 can be calculated as at 15 megapascal and 625. You go to the steam table and calculate, like for the superheated steam, you'll get it around 3648 kilojoule per kilogram. And then H4 is the exit of the steam if it was exit of the steam from the turbine if it was isentropic. So this can be calculated at 10 kilopascal and the entropy and using an isentropic process S3 equal to S4. We calculate the value of you calculate the entropy at the state point 50 megapascal and 625, and this will be same as that of 0.4. Therefore, for these two conditions, we calculate the value of the enthalpy H4. So H4 will be equal to, from the steam table, we can get it to be 2139 kilojoule per kilogram. So the corresponding efficiency, this difference multiplied by 0.87, that will give you the corresponding value of the work output from the turbine. So that is equal to 1313 kilojoule per kilogram. That is one part of the network. And the second part is work input required in the pump. So that will be equal to the specific volume of the fluid, as I have mentioned, since it pumping power is actually equal to the specific volume into the delta P pressure. It is in compressed fluid. We are dealing with incompressible fluid, so there will not be a change in density as such. So if there is no change in density, the inverse in the reciprocal of the density is actually the specific volume. So it remains the same. So we can assume that there is no huge difference between the specific volumes. So specific volume multiplied by delta P, that will be giving us the isentropic power input, but the actual power input will be higher than that of the the isentropic power. So we have to divide it by the isentropic efficiency. So the specific volume at the condition of 10 kilopascal, saturated liquid specific volume, saturated liquid specific volume at 10 kilopascal, and that will be equal to, you can approximate it to be 0.001 meter cube per kg. And the two pressures are given at the input and the output. So there will be output, it will be 15 megapascal. So we can write it to be 15 into 10 cube kilopascal, and the input is 10 kilopascal. So we can get in the result in terms of kilojoule per kilogram. And the efficiency, pump efficiency is given as 0.85. So this will be equal to 17.64 kilojoule. So if you compare between the pump power input, work input, and turbine work input, work output, that is a significant change. So its pump work input is very minimal compared to that of turbine work output, and that is due to the pressurizing that we happen and the heat input that we give to the boiler. So superheated steam, once expands, it will be giving much higher work output compared to the work input which happens for a liquid water at a low pressure compared to the input to the turbine. So therefore the net heat input, okay, sorry, and then we have to calculate the denominator. So it's not net heat but rather the heat input. The heat input to the boiler uh, Qin can be represented as H3 minus H2. But the point H2 is the isentropic point where the enthalpy we need to calculate. And H3 minus H2 will be the heat input in this case. So this will be equal to H3 minus H2 dash. H3 minus H2 dash. We do not know the state point H2 dash right now. That you have to calculate from the pump efficiency. So pump isentropic efficiency, get it as H2 minus H1, the actual power of work input divided by the ideal the ideal work input, that will be equal to H2 minus H1 minus of actual work input H2 dash minus H1. So using this, we can calculate the value of H2 dash. So H2 dash will be equal to slight rearrangement. So H2 minus H1 divided by efficiency of it. This is one way that you can calculate the a method to calculate the enthalpy of water at the exit of pump. So this is one way, but other way that you can do is we can actually use the state points that is given in the problem. So in the problem, it is mentioned the state point 2 will be at condition of temperature 35 degrees Celsius and pressure 15 megapascal straight away given. So you can calculate it straight away, the enthalpy at the state point 2. So that will be equal to 160 kilojoule per kilogram. The enthalpy for liquid, subcooled liquid at 35 degrees Celsius and 15 megapascal. So therefore, the heat input to the boiler will be equal to 3 dash minus H3 minus H2 dash. That will be H3 we have already calculated in the previous case. So it will be 3648 minus 160. So 34 double heat kilojoule per kilogram will be the heat input to the boiler. Therefore, the thermal efficiency will be equal to the work net divided by heat input. So that will be equal to the numerator will be work turbine minus work done divided by Q input. So that will be equal to 1313 minus 17.64 divided by 3488. So that will be equal to 37.13%. So that will be the first step. The efficiency we have calculated to be 37%. So straight away, if you know the state points, you can determine that using the basic cycle analysis. You need the total work output and heat input divided by heat input will get the value. Now you have to calculate the power output if you know the mass flow rate. So it's given the mass flow rate is 15 kilogram per second. You multiply the net work and you with this mass flow rate, you'll get the net power output. One three one three minus 17.64. So that would give us the total power 19.425 meters. So this is basically a starting problem for steam power plant. You have a cycle diagram as well as the TS plane and the depiction of the cycle in the TS plane. You need to calculate the efficiency of the cycle and the total power output. Total power output is directly calculated after you get the network output. Work output divided multiplied by the mass flow rate will give you the total power output. Work will be in terms of kilojoule per kilogram. So in order to calculate the cycle efficiency, you need to calculate the net work output and the heat input. So net work output depends upon the turbine work and the pump work. So since isentropic efficiencies are given, you have to calculate the work given by the turbine and the actual work input to the pump. So there can be multiple ways. Since the state points are given in this problem, we can straight away calculate a few entities. But if it was not given, I have also tried to explain how to calculate a few state points using the isentropic values. Now we can move to the next problem. This is based on a Rankine cycle. Look into it. I'll also try to solve it in a couple of minutes. So it's a steam power plant that operates on ideal Rankine cycle. Steam enters a turbine at 3 megapascal, 350 degrees Celsius, and the condenser is at 10 kilopascal. We have to determine the thermal efficiency of the plant. And thermal efficiency is a superheat if the steam is superheated to 600 degrees Celsius instead of 350 degrees Celsius. There are two particular cases, and we are trying to see we are trying to reduce something out of this question. But before that, before going into that details, let us solve these two parts of the problem independently and look into the results. And the results will show something that that deduction from the results will be one of the most important inferences of these kind of problems. So what we can do to improve efficiency is one main question that everyone has to answer. And this is one way in which it could be done. Yeah, so we can try to solve the problem. The first part, the efficiency calculation, it's very straightforward. Just like the previous case, we have to follow the methodological approach, uh, algorithmic kind of algorithmic. So there is this steamed TS diagram, and here the pump work. It's an ideal cycle, so there is no issue of the turbine power, turbine and the isentropic efficiency, turbine and the pump isentropic efficiency in this case. Therefore, question 3 is at 350 degrees Celsius and 3 megapascal, and there is this heat input Q in, and there is this heat output Q out, and then this happens at 10 kilopascal, and this state point is 4, 1, and this point is 2. So thermal efficiency, we have to calculate that is equal to net work divided by heat input. And so this is a cycle. So what you could do is that this is a cycle and work network can be written as the net heat input of a cycle. So that will be equal to heat in minus heat out divided by Q in. So basically 1 minus Q out by Q in. The Q out, that will be equal to H4 minus H1. That is the heat output, that is a condenser heat output. You need to calculate the state points to get H4 and H1. And then Q in will be H3 minus H2. That is the boiler heat input. And thermal efficiency will be equal to 1 minus of Q out divided by Q in. For that, we need to calculate the state points. So for that, we calculate the enthalpies at the state points. We need H4, H1, and H3 in this problem. So we calculate the enthalpies at each and every state point. So state point, we need H4, H1, H3, H2, all the 4 state points enthalpies we require. So state point 1, that is at the saturated liquid condition. So pressure is given as 10 kilopascal, and for that we'll get the enthalpy H1 from a steam table as the saturated fluid enthalpy at 10 kilopascal. That will be equal to 191.81 kilojoule per kilogram. So will be is the specific volume at the saturated liquid condition at 10 kilopascal. So that will be equal to 0.001 meter cube per kg. At the state point 2, the pressure will be given as 3 megapascal. And since it's an isentropic process, S2 will be equal to S1. And you can calculate the enthalpy at that particular point using this step. Or otherwise, as I had explained in the previous step, there is another way in which the point H2 enthalpy can be calculated. That is using the work. So work done in the pump, it's an isentropic process that will be equal to specific volume multiplied by the change in the pressures. So you know the pressures at the top and bottom, that will be equal to 0.001. That is a specific volume at 10 kilopascal multiplied by, we assume that there's no compression of the fluid and the specific volume of the density remains the same for the liquid. So saturated liquid condition, and the pressures is 3003 megapascal at the top, 3000 kilopascal and 10 kilopascal. So that the value will be equal to 3.02 kilojoule per kilogram. So that is basically the difference between this is actually the difference between the exit and the inlet of the pump H2 minus H1. Therefore, we already know H1, so H2 will be equal to H1 plus work done on the pump, that will be equal to 191.8 plus 3.02, 194.883 kilojoule per kilogram. So this is one way. This is the way. This is the different approach compared to the third problem that we are seeing. And then state point 3, it's superheated steam. Straightforward. You have to go to the steam table and look for the enthalpy corresponding to these state points. Temperature 350 degrees Celsius and pressure is 3 megapascal. Superheated steam. We get H3 is equal to 3.16.1 kilojoule per kilogram. And then S3 will be equal to entropy at that particular point will be equal to 6.74. The reason for calculating this entropy is that we need to actually determine the entropy. We need to determine the state point 4, the exit of the turbines enthalpy using the isentropic approach. So at the state point 4, we know the pressure that is equal to 10 kilopascal, and the entropy is the same as that of S3, that will be equal to 6.74. We know two conditions. We know the pressure at the exit and the entropy at this particular point. So we can try to calculate the dryness fraction or the quality of the steam at the exit. So since this is saturated condition, we require two properties. One is dryness fraction or the quality of the steam, how much mass of the vapor divided by total mass of the vapor plus steam. We for saturated condition, we require additional one property. And what we can do is that the state point for enthalpy will be equal to so how we can get the enthalpy is slightly tricky. We have to calculate the dryness fraction using the entropy. So what we can do is that the state point for entropy will be equal to the saturated fluid and entropy at point 1 plus the dryness fraction multiplied by the saturated gas entropy corresponding to 10 kilopascal, and this is also 10 kilopascal, minus Yes, fluid at 10 kilopascal entropy. You already know the value of S4, 6.74 kilojoule per kilogram Kelvin. And then you can calculate it from the steam table, the entropy corresponding to saturated liquid at 10 kilopascal and the saturated gas corresponding to 10 kilopascal also you can calculate. And you will get the value of X. So I get X as 0.8128. That is the quality of the steam. And using a similar formula, we can calculate the enthalpy of the state point 4. So H4 will be equal to the enthalpy of the saturated fluid at saturated liquid at 10 kilopascal plus X into HFG, the enthalpy of vaporization at 10 kilopascal. So you can go to the steam table and find these two properties. So HFG will be equal to H gas at saturated gas, saturated gas minus H saturated fluid at 10 kilopascal. So we know the value of X, that is 0.8128. So we'll get H4 as 2136 kilojoule per kilogram. So we plug in the values here. So H4 minus H1 will be 2136 minus, we already got H1 will be 191.8. The value will be 4.3 kilojoule per kilogram. The heat input value in the boiler, that will be H3 minus H2. Straight away we can substitute the value. H3 will be 3116.1 minus 194.83. So the value will be 2921 kilojoule per kilogram. So efficiency will be 1 minus Q out minus Q in. That will be equal to 33.4%. That will be the efficiency of the Rankine cycle operating between these two state points. The second problem is where the steam will be superheated in the boiler, giving much more heat to 650 degrees Celsius instead of 350 degrees Celsius. And we have to see 600 degrees Celsius instead of 350, and we have to see what changes does it make to the thermal efficiency of the cycle and what inference that we can deduce from it. So the state point two for the question number two, it's kind of same. The only difference here is that instead of 350, it will be heated up to 600 degrees Celsius. So if this was the initial case, the new case will be so the new case will be you heat it up even more to 600 degrees Celsius, and then you condense it straight away and to the same condenser temperature. So basically, we have to calculate the new H3. In order to calculate the efficiency, you need to calculate the new points H3 dash and H4 dash. So the H3 dash corresponds to 3 megapascal and 600 degrees Celsius, and that will be equal to 3682.8 kilojoule per kilogram. In order to calculate the state point 4, we need to calculate the entropy, isentropic turbine. So S3 will be at the state point is superheated condition 7.51 kilojoule per kilogram Kelvin. So S3 will be equal to S4. S3 dash will be equal to S4 dash. This is dash isentropic turbine. So H4 dash will be calculated at 10 kilopascal, and S is equal to 7.51 kilojoule per kilogram Kelvin. For that particular condition, we need to find the dryness fraction. Where exactly does it fall on the line? So we can calculate S is equal to SF plus X into SFG. So X will be equal to point. So from this we can calculate at 10 kilopascal. S will be 7.51, and SF and SFG you have to calculate at 10 kilopascal for the fluid, and you'll get X as 0.915. You use that X to calculate H4. H4 will be equal to HF plus X HFG at 10 kilopascal. This is enthalpy of vaporization at 10 kilopascal, and this is enthalpy of the saturated liquid at 10 kilopascal, and X will be equal to 0.915. Plug in the value here straight away, and you get H4 is equal to 2380.3 kilojoule per kilogram. Therefore, the efficiency is equal to 1 minus of Q in, Q out divided by Q in. That will be equal to H4 minus H1. That is new state points H4 dash minus H1 dash. So I have been using it interchangeably X4 and H4 dash. So this is a new statement H4 dash minus H1 divided by Q input will be equal to H3 dash minus H2. So H1 and H2 remain the same from the previous case, and if we plug in the H4 dash and H3 dash value, we go from here and we will get the value as 3488 equal to 3743%. So if you try to observe, in the first part of the problem, we got an efficiency of 33.4%. And in the second part, we got an efficiency of 37.3%. Only by increasing the exit of the boiler or the input of the steam to a much more high temperature region. So basically steam condition, it's much more superheated at the input of the turbine. So why does the efficiency increase in this case? We only change that. Then also another point to notice that the quality of the steam in the first case, it was 0.8128, 80% vapor. And in the second case, that is a much more higher vapor. So it happens, and its value is 0.915 in the second case. The dryness fraction moves towards the right. So what can you infer from this two parts of the problem? So basically, this is a concept of higher temperature of heat addition. So if you have looked into the entropy equation, it always have a temperature of heat addition. So the same heat that we deliver at a higher temperature compared to the same heat that we deliver at a low temperature, there will be some difference in the entropy or the available energy. So So what I meant to say is that when we deliver the same heat at a higher temperature compared to a lower temperature, the percentage, the fraction of the work that is useful, the useful energy from out of this work, out of this heat is quite high at a higher temperature. This is because the irreversibilities due to the temperature gradient, we assume that the temperature of the high temperature heat sink is a constant. And from there, when we try to add heat into the boiler to the steam side, the temperature gradient will be less when we are delivering it at a higher temperature. So what that means is that the irreversibilities associated with the temperature gradient uh, will be uh, will be less in the case of a high temperature one. So I know that it can be quite confusing. What I meant to say is that consider two cases, and we take, instead of going the constant pressure process, we take an average temperature that might be at the point where the heat will be added. So in the first case, when the fluid was heated up to 300 degrees Celsius, let's say the average temperature, it would, the exit point would have been 300. So, but we actually shifted the curve slightly upwards and take it to be a constant temperature of heat addition process. So for the first case, we can say it might be having an average temperature of heat addition, say 275 degrees Celsius. So the actual input to the boiler was 300, but the sorry, input to the turbine was 300 50 and the input to the boiler was at a lower temperature. So we actually shifted this curve so that it will be a replica of uh, the actual process. And in the second case, for in the second case, the whole temperature of heat addition process shift upwards. So corresponding to, say, a 600 degrees Celsius, maybe say the average temperature of heat addition, or the average temperature in the boiler was, say, maybe say 500 degrees Celsius. It's an approximation. It's not qualitative. So it's, sorry, it's not quantitative. It's slightly qualitative explanation that I'm trying to give here. So basically the temperature of the heat addition increases in these two processes. Say the high temperature heat pump heat source. The high temperature heat source will be maybe at 800 degrees Celsius. So the heat addition has to take place from 800 degrees Celsius to the corresponding average temperature of heat addition. So in this case, the temperature gradient would be, say, 300 degrees Celsius. And in the second case, the temperature gradient, we are not changing for the, we are fixing the analysis, the temperature of the heat source temperature. It's a qualitative analysis. Not the accurate, not the actual values. We have to note it. So the here the heat temperature, the difference between the source as well as the average temperature of the boiler is higher, maybe 525 degrees Celsius. So when the heat transfers, the same heat transfers at the when the temperature gradient between the source and the boiler is high, there will be irreversibilities associated with it, and the amount of available energy, or the amount of useful work that we can get out of this heat, will be minimized in that case. It takes into consideration the temperature, the average temperature of heat addition, basically. And so the heat added from 800 degrees Celsius to the boiler at 500 degrees Celsius will be having much higher component that can be made into useful work. And that is the reason why we see an efficiency increase between two cases, the second case and the first cases. There's a significant increase in the efficiency in the second case, only because of this that we are increasing the average temperature heat addition. So if you try to denote this as efficiency of the Rankine cycle, we try to denote it as in a simplified term analogous to a Carnot cycle. So 1 minus of T divided by T high. This is the average temperature of heat rejection and the average temperature of heat addition. So basically, when the average temperature of the heat addition increases, the whole term decreases and the efficiency increases. So when this increases, this increases. So it's a keeping every other temperature and the state points constant. So as temperature of the state points constant, we'll get a higher efficiency for the Rankine cycle. So that is the overall analysis that we could see. Higher average temperature of heat addition gives efficiency. So in this problem, we just compared between two cases of heat addition, where one is heated to 350 degrees Celsius and the other to 600. And we compared between their efficiency and we found out that the temperature of heat addition has got significant impact on the efficiency. So higher temperature of heat addition corresponds to lower irreversibilities, and resulting in a higher efficiency. Okay, that completes this problem. And now we can move to the next part. Next question. It's a very straightforward one. It's second part of the problem that we have to do. Let me compare it with outside. So consider a steam power plant operating on the simple ideal Rankine cycle. Steam enters the turbine at 3 megapascal and 350 degrees Celsius and is condensed in the condenser at a pressure of 75 kilopascal. Here to determine the thermal efficiency of the cycle and then compare it with the Carnot cycle that operates within the same temperature limits. It's a very similar problem to the previous case. There is nothing much difference. The only point of consideration that we need to make is how to calculate the Carnot efficiency and how to compare it with the basic case. So it's in a way kind of reiterating what we have seen in the previous case. We just need to calculate the efficiency of the thermal efficiency of the cycle. That is basically work net divided by heat input, that will be equal to H3 minus H4. It's an ideal cycle. So literally it's the same as out of the previous case. No efficiency, no isentropic efficiency consideration we need to make here. Everything is straightforward. Yes. So H3 minus H4, that is a work turbine, and then work pump will be equal to divided by Q. So H3 we can calculate the H3 value at temperature of 350 degrees Celsius and 3 megapascal, 350 degrees Celsius and 3 megapascal. H will be equal to 3116 kilojoule per kilogram, and S3 will be 6.745 kilojoule per kilogram. And from there we can calculate S4 will be equal to S3 and calculate X. X4, that will be the quality of the steam, that will be 0.88, and it's basically same as out of the previous case. I'm not reiterating the steps again. It will become boring. X4 dryness fraction, the quality of the steam at the exit will be equal to 0.8, and using that we can calculate H4 as HF plus HFG at lower point, that is 75 kilopascal. So that will be equal to 2389 kilojoule per kilogram. Now coming to the work input to the pump, that will be equal to H2 minus H1. That will be equal to can be written as the specific volume of the fluid at the 0.1 multiplied by the pressure difference. So that's basically the same 0.001 into 3000 kilopascal minus 75 kilopascal, that will be equal to 3 kilojoule per kilogram Kelvin. So you get everything that you require here, and then you need a heat input. You require H3 and H2. So you can calculate the value of H1. H1 is the specific fluid HF at 75 kilopascal. The specific enthalpy of the saturated liquid at 75 kilopascal, that will be equal to 385 4 kilojoule per kilogram, and H2 will be equal to 384 plus 3 kilojoule per kilogram. So that is H1 plus work done pump, that will be equal to 387 kilojoule per kilogram. So we have got everything to solve this problem. So all the four enthalpies we have got straight away, and then we substitute that in this problem. So efficiency will be equal to H3 minus H4. Heat input will be equal to H3 minus H2. We substitute the value, it will be 3116 minus 2389 minus 387 minus 384, that is 3 kilopascal, the 3 kilojoule per kilogram, and then on the bottom point 316 minus 387, that will give you an efficiency of somewhere around 26.5%. So that is the first part of the problem, just following the same method as previously. It's a kind of the same process, or the same algorithmic approach as that we have seen in the previous questions. And then to calculate the Carnot cycle thermal efficiency, you take into consideration, you assume that the cycle operates between 2 points, and the top point will be at 350 degrees Celsius, and the bottom point will be at its isothermal process, basically at the minimum will be the saturation temperature corresponding to 75 kilopascal, that will be equal to 365, somewhere around 81 degrees Celsius. So that's straightforward. So it can be written as TL divided by T high, so 1 minus 350 degrees Celsius, that will happen at 623 Kelvin, and T low, this you can say maybe 91 degrees Celsius. So the issue, so it was around corresponding to 75 kilopascal. The saturation temperature is corresponding to 75 kilopascal. That is 364 Kelvin. So we'll get an efficiency of 41.5%. So that shows. So this is the case, is the maximum possible that can be attained between this to the temperature of heat additions. So here we assume that there is no irreversibility associated with the heat addition. So the temperature of the heat addition process remains a constant at 350 degrees Celsius. But there in the previous case, in the case of thermal cycle, though the highest point will be at 350 degrees Celsius, the average temperature of heat addition will be at a low. So that results in a lower heat, the lower efficiency. So the lower term TH, T higher average heat temperature of heat addition, that will be lower in the case of the Rankine cycle, and that results in a lower efficiency compared to a Carnot cycle. So basically, irreversibility is due to temperature difference. The irreversibility to due to the temperature difference of heat addition. Write it somewhere else since it becomes so congested. Greater than eta Rankine. Irreversibilities in the irreversibilities in the Rankine cycle due to temperature difference of heat addition is the source of irreversibility, and the amount of unavailable energy increases due to this temperature gradient of heat addition. So basically that is the difference. This whole exercise was to show that the Carnot cycle efficiency is greater than the Rankine cycle efficiency due to this irreversibility associated with the Rankine cycle. Now we move to a few multiple choice questions. Look into the problem. Question number 6. In steam tables, entropy is 0 for which of the following condition? A saturated vapor at 0 gauge pressure, saturated liquid at 0 gauge pressure, saturated vapor at 0 degrees Celsius, and saturated liquid at 0 degrees Celsius. Entropy is 0. If you look into the steam table, which is the datum for determining the entropy. So the TS diagram, this is the liquid condition vapor. So this is corresponding to 0 degrees Celsius. What will be the entropy? So it has got nothing to do with the pressures, but it has got to do with the temperatures. It is at 0 degrees Celsius in the liquid that is considered the datum point, where the entropy will be equal to 0. And every other point's entropy will be calculated with respect to this datum point. So the answer is saturated liquid at 0 degrees Celsius. This is a question just based on the observation. This is how they take it so that everything else can be considered based on this. Saturated liquid at a 0 degrees Celsius. That is considered to be 0. In ideal terms, entropy will become 0 only for 0 Kelvin. But here for this analysis, the difference in the entropy is that matters. So every other point's entropy is considered with respect to this datum point. In this problem. Another multiple choice question. Try to solve it. I'll also try to solve it. Yeah, look into the seventh problem. It's a multiple choice question. For the generation of electrical power, why are steam power plants more popular? The work output of the turbine is smaller than the work input of the pump. Work output of the turbine is equal to the work input. Work output of the turbine is greater than the work input to the pump, and none of the above. It's pretty self-explanatory. So the question number, the option 3 is the right choice. Work output of the turbine is greater than the work input to the pump. So in this case of generation of electrical power, the high pressure steam expands in the turbine. High pressure, high temperature steam expands in the turbine to produce work. There should be some work input to the case. The second law of thermodynamics says that uh, the entire heat cannot be converted into work. Therefore, there will be some additional work input that needs to be done to get or in some additional work input, or what I meant to say is that there will be some heat rejection that will happen in this process in the condenser. So what we can try to do is minimize the whole thing, try to attain the maximum possible efficiency that is achievable. That even then, that will be that should not violate the second law of thermodynamics. So high pressure steam expands in the turbine to produce work, and this work done in the turbine is significantly high compared to work done in the pump. Why? In the pumps, since we are dealing with liquid water, it's basically incompressible. That means that its volume doesn't change. It's almost a constant. So the work pump could get written as a specific volume multiplied by the change in pressure. So that it can be pressurized. The liquid can be pressurized by providing very less work because the specific volume is very less. The change in specific volume is less, and the actual specific volume is also significantly less compared to the compared to a gas because of high density. So this quantity is less. There will not be a change in the specific volume in the first place, and then the total quantity will be less, very less compared to the turbine. Imagine if it was a compressor and the incoming fluid was gas. So the same explanation that I tried to give in the first problem happens. So in that case, the gas is compressible, so there will be a change in the volume as well. So the total work input will be a combination of the amount of work required to compress the gas and then to pressurize it as well. So the volume change as well as the increase in the pressure, both of them needs to be accounted. And for that, we need to take into consideration the enthalpy change in the process, and the work input will be high compared to that of a pump. So basically, this is the reason why the net work will be approximately equal to work done as work done in the turbine, as work done in the pump is very much less than that of the work turbine. So this is the reason why steam power plants are more popular. I hope you understood it. Now we can move to the next problem. It's also a multiple choice question. Yes, the steady state flow equation reduces to the heat transfer Q dot uh, equal to m mass flow rate into H2 minus H1 for which of the following cases when change in potential and kinetic energy is neglected. So the steady flow energy equation, if you try to recollect, that will be equal to m dot into h1 plus b1 squared divided by 2 plus gz1 plus q plus w is equal to q plus w was a state point 1 and state point 2. If you compare between two state points 1 and 2, and then the m dot 1 and m dot 2 into h2 plus h2 squared divided by 2 into gz2. So this is a general form of the steady flow energy equation where you consider the enthalpy flow work and the kinetic energy, potential energy, the heat input to the system, the work input to the system, heat given out of the system, work output of the system that interacts with the second state, and then m2 and h2 plus v2 squared. Similarly, at the state point 2, the same energy components. So what you could say is that heat is an input to the system. So Q1 input. So if you assume that there is only heat input, so this particular term remains, and we ignore the velocity and the potential energy term that will be there. And if you say that there is a work output from the system, so that will be work out plus work out plus m dot into h2. So basically, this system will be having a heat interaction that is incoming to the system, and a work output that will be going out of the system, that is positive onto the right hand side. So a general equation can be simplified in this form. So when exactly this particular equation reduces to this particular equation when the output work will be equal to 0. So we need to consider the device where the output work will be equal to 0, and there's a heat transfer that happens in this during this process. So consider a case of nozzle. Is there a work output? I don't think so. There is no work output as such. So is there a heat input? No. The nozzle actually what it does is that it converts a kinetic energy, the enthalpy change in terms of the kinetic energy change. So initially at the inlet of the nozzle, the velocity will be kind of 0, and as it moves forward, the velocity increases, taking the enthalpy change into consideration. But here, since the potential and kinetic energy are neglected, so the enthalpy, we could assume that m dot h1 is equal to m dot h2, neglecting kinetic energy changes. So this is not a solution. Then the turbine, we know it's a work producing device, so this can't be right, that's wrong. Then compressor, work input device, so it can't be right. So the only option that is available is heat in boiler. So in boiler, what happens is that the heat input will be equal to the heat input will be equal to m dot the heat input will be equal to heat m dot into enthalpy change, m dot into h2 minus h1. So this is the right option. This is the boiler, the same boiler that is depicted by the process 2 to 3. So it's a straightforward problem to identify the component where the steady flow energy equation reduces to this form. So that is boiler, where it's a heat interacting device. Now we can move to a numerical type problem. So in this problem, as you could see, it's a case of it's a similar problem that takes into account the steady flow energy equations. We need to consider. So I'll read the problem aloud. Liquid sodium flowing at 100 kg per second enters a heat exchanger at 450 degrees Celsius and exits at 350 degrees Celsius. The specific heat of sodium is 1.25 kilojoule per kilogram Celsius. Water enters at 5,000 kilopascal and 20 degrees Celsius. The enthalpy of water inlet and outlet are 88.7 kilojoule per kilogram and 2792.8 kilojoule per kilogram respectively. We need to calculate the mass flow rate, minimum mass flow rate of water, so that water does not completely vaporize. Basically, a heat exchanger which transfers heat from one device to another. Liquid sodium has got higher melting temperature as well as uh, boiling point. So try to solve it and also try to solve it. It's a straightforward problem. We need to make sure that the water does not completely vaporize. So for that, what should be the case? The specific heat of the sodium is lower than that of the steam. But the reason why the specific heat, the sodium is actually taken instead of steam in certain type of heat exchangers, which are used in the fast breeder nuclear reactors, is that it has got a higher conductance, thermal conductance. The thermal conductivity of the sodium is very much high. So, and also the second part is that its boiling point is significantly high, 83 degrees Celsius compared to water. So we did not raise the temperature of, if we had used a higher side, if we had used a higher side temperature source as a high temperature steam, we need to actually uh, increase the increase the pressure so much, so that we can attain that particular temperature. The liquid sodium, even before getting evaporated, we can attain a higher temperature of 883 degrees Celsius. So it retains its liquid form at that temperature. So what I meant to say is that if we were to use water, if we go to 883 degrees Celsius at the ambient at the ambient pressure, so it will be in the vapor form, superheated condition. But if you uh, pressurize the liquid, it will it can still exist in the liquid form, at 883 degrees Celsius. So for that, that pressurizing energy is required. You have to exist in the two-phase condition in 883. So you go inside the vapor tube or left of it to have the liquid state. So a liquid state will be having higher conductance as well as higher conductivity as well as higher specific heat. So the reason why we go to the liquid sodium is because of its higher thermal conductivity as well as the ability to be in the liquid state at higher temperatures. So I will have to retract what I have mentioned slightly before. So it's a straightforward problem. Minimum mass flow rate of water so that the water does not completely vaporize. So inlet and outlet conditions of the water are given. So both are in the water phase. So the liquid sodium side energy you can completely calculate. So liquid sodium side, that's basic energy balance. The heat transferred from the liquid side, sodium, that will be completely taken by the water to evaporate. So if it shouldn't evaporate, the question says that it's enthalpy of water at inlet and outlet. Water enters at 5,000 kilopascal and 20 degrees Celsius, and the outlet enthalpy is given as 2798 kilojoule per kilogram. So we know that. So the liquid sodium side energy, heat that will be taken by the water. So m dot water multiplied by the outlet enthalpy, H outlet minus H in, will be giving you mass flow rate of the liquid sodium multiplied by Cp of sodium multiplied by the delta T. So it enters at 450 and leaves at 350 degrees Celsius. Cp is given as 1.25 and m dot sodium is 100 kg per second. Similar, and we need to calculate the steam, the water mass flow rate. H outlet is 2792.8 minus 88.7 kilojoule per kilogram. So inlet, you know the enthalpy, the outlet also you know enthalpy. So what should be done? So basically this is a straightforward problem. You have to calculate. So it's mentioned that it's water. What to happen? The question says that there will be energy transfer from the liquid desiccant side, from the sodium side to the water side. And says that water exit condition is water outlet condition is in the liquid phase. So it's already given. We just need to calculate the mass flow rate of the water. In this case, it will be you'll be getting it as 4.6 kilogram per second. It's a straightforward problem of energy balance. That completes the session for this week. In this week, we have seen a few numerical type problem and the multiple choice questions based on the steam power plants and the Rankine cycles. So we continue the analysis of the steam power plant in the next week as well. So we'll look into the modification that we will be making at the steam power plant to make it much more efficient. We'll look into design modifications, reheat cycle, and the starting of regeneration as well. That will be taken care in the week after the next week. So if you have any doubts, you can post in the post forum. Thank you.